Oh man, I can't wait. You know what this is about to be? This is my favorite section in all of calculus right here. Look at that integral. That looks like a pretty challenging integral right there. All the other techniques up to this point, we can't integrate that sucker, man. I got to put on my thinking cap to figure out how to integrate this sucker, man. Here's what my thinking cap just says, man. This is a beautiful section that this integral right here, that has no trig in it whatsoever. My thinking cap just told me the only way to solve that integral is to insert trig into that problem right there. I know this is about to be your favorite section too, man. We're gonna like just create trig inside this integral in order to solve that sucker, man. So it's a pretty powerful thing. Listen, this technique works in a lot of different scenarios. It's a very powerful thing that works. It doesn't even have to be like a perfect square. It could be like a 7 minus x squared or something in there. But this works in a lot of different things where trig substitution pops up, right? I will tell you ahead of time, a little bit lengthy problems, but students typically pick up on this really well, and we usually crush this stuff on a testing situation. You just got to make sure you bring it and you practice it as much as possible right here. So I'm going to show you a very systematic approach. It won't be necessarily like the last section where you got to decide, how do I integrate this? It's going to be very systematic where you're going to recognize the pattern and then follow the steps that I give you. And usually once you know how to do a couple of these, you know how to do all of them. You just got to make sure you practice that, all right? So what we're going to recognize inside these integrals are these patterns to the side, where the a is the number part that's being squared, the u is the variable part that's being squared. So if you see like a number part squared minus a variable part squared, we're going to make this trig substitution with the sine function, right? Variable part squared minus the number part squared, we'll use the secant function, and then your variable part squared plus the number part squared, we're going to use that tangent function right there. So we want to make sure we got all three of these memorized. Good news is there's only those three. That's it, all right? So we just got to make sure we have all those down. And then here's how this is going to work. Very systematic approach there. And you're going to do this same approach pretty much on most of these problems, right? But just sometimes in the middle of the problem, the integral can get a little bit different, right? But when I recognize a squared minus u squared, that's this pattern right here where I'm going to jot down for myself that, hey, the a is my number part that's being squared, and the u is that variable part that's being squared. And so what you're going to do is you're going to make an initial trig substitution step. Right here, it says u equals a sine of theta. So my u is equal to x. So I'm going to go x equals a times sine of theta. My a is 5, so I'm going to go 5 times sine of theta. All right, so that's your initial trig substitution step. So just recognize the pattern, use the correct one, make sure you know which is which, right? So, and then once you get that down, then we're going to do this. We're going to take the derivative of this thing. We're going to find the dx. So we're going to do the derivative sine is going to be cosine. And then after this, what we're about to do is we're going to do item for item substitution. Everything is going to be accounted for. So no balancing or anything like that. Item for item substitution. So this 10 is just kind of there. All right. So I'm going to carry that down. And we got the integral. Now we have this x squared. My x is equal to this. So I'm going to take that 5 sine of theta. I'm going to insert that for all the x's in my original integral there. We're inserting trig into the problem. So when I plugged it in and I square, that'll give us a 25 sine squared. And then we have the square root of this 25 minus that x squared. So again, this is my x. I'm going to plug it in there and square it. I'm going to get another 25 sine squared theta. And then what you got to also remember to do is please remember to substitute for that dx. That's why we take that derivative. So the dx is equivalent to 5 cosine of theta. So far, I think you'll like that. Recognize the pattern. That'll be pretty easy, right? Take the derivative and then just plug in. And you got nothing but thetas in here at this point. Now, on just about every single one of these problems, you're going to have a parentheses or a square root of some sort. And I want you to go to that parentheses or inside of that square root. I want you to simplify that. Sometimes you'll go straight to the Pythagorean identities. Most of the time, there'll be like a GCF in the Pythagorean identity that you got to do there. So that's what I'm going to do. I'm going to just go to that square root. I'm going to simplify that. I can factor out a GCF over 25. That'll leave us with a 1 minus sine squared. I can then simplify that using my Pythagorean identities. That's going to be 25 cosine squared. But notice that's all underneath that square root. I'm going to square root that and get 5 cosine of theta. And then what I notice here is that I have a 5 cosine of theta on the top and the bottom. So those completely cancel out. Now they won't always completely cancel out like that. Sometimes nothing cancels out. You got just a numerator in there, but you just, whatever happens, happens. All right. You just kind of work with that and just make sure you gather everybody, but those cancel out on that one. So this 10 over 25, I'm going to pull that out now. And I'm going to have a 2 over 5 out in front of that integral. And then what I have left is a 1 over sine squared. Now, when I have a 1 over sine squared, I typically just kind of gather everybody and look at that. When I have that 1 over sine squared, make sure you don't leave anybody else behind there. I can't integrate a 1 over sine squared, but I know I can make that a cosecant squared, because I'm supposed to know how to integrate that cosecant squared, right? So now I successfully have turned this into something that I can integrate. So I'm going to integrate that now. When you integrate cosecant squared, we get a negative cotangent. That's one of your reverse derivatives, because the derivative cotangent is a negative cosecant squared. So since you don't see that negative there, put that negative right there. Now, if you think about it, we're done with the calculus right here. But you're thinking, hey, this probably isn't done yet because you have thetas in the problem, not x's. So now we're at the part of the problem where we got to get our x's back into the problem, right? And the nice thing about this, the beautiful thing about this trig substitution is you're going to do the same thing every single time. There's one way to get your x's back in there every single time. Here's what I want you to do. I want you to always go back to your initial trig substitution step, that x equals 5 sine of theta. And I want you to isolate that trigonometric function, all right? So I want you to solve for that trig function. I want you to make that sine of theta equals x over 5, and we're going to draw ourselves a right triangle. Any old right triangle. Could go this direction, this direction, but you just got a right triangle right there. And we're going to set this triangle up. So you're going to put your theta right there, and then it says sine of theta equals x over 5. You know your SOHCAHTOA, right? That's going to be opposite over hypotenuse. And you can use your Pythagorean identity to do this x squared minus this squared to get this as radical 25 minus x squared. Now, what happens on just about every single problem is that this thing that you get is kind of inside that integral someplace. The only time that won't happen is if there's like a GCF that could be potentially done at the beginning that you ain't got to worry about. You might get the simplified version, not the one that they have there. But most of the time, you'll get that inside part of that integral there. All right, and then you're just going to use SOHCAHTOA to get your x's back in the problem. So you know that tangent is equivalent to opposite over adjacent, which means your cotangent then is going to be the reciprocal of that, the adjacent side over the opposite side. So you got this negative 2/5, and then your cotangent then you're going to, of the theta, you're going to do the adjacent side over the opposite side. So that's going to be your radical 25 minus x squared all over that x, and then we have our final answer. So I just have this, I'll just rewrite it like this. You got your plus c, and then we're done. So there's your trig substitution. So you're gonna see very similar steps on just about every single one of these problems, which is why students have kind of told me they like that, because they like that systematic approach where they recognize the patterns as good as kind of, to me, I love these integrals because it's kind of like a puzzle. You know, you just see those patterns in there and you just work that stuff out there. Just sometimes the integral, you know, if you get to this point, you can't integrate cosecant squared because you don't know your basic trig, that's going to mess you up. Sometimes when you get here, you have a harder integral. You might have that things from the past section where we did like the choose the odd power, save one, convert the other, and you might have to deal with some other stuff right there. Sometimes if you forget to substitute for that dx, you might get something here really easy where I can't give you any partial credit points, or you might get something that's impossible to integrate because you forgot to like do that stuff right there. But recognize the pattern, make the initial trig substitution. Like, you always realize how tragic that would be if you just did like 5 secant of theta instead of sine of theta. That whole entire problem is going to be wrong. So you got to make sure you got those 3 things down. Make sure those are fresh in your head, right? So there's one example, and then there is something different that happens at the end of this example. I gotta show you one more example and show you how to handle this stuff at the end, and then we'll be good there, okay? So when I look at this, not a u to u, all right? And so I see a variable part squared minus a number part squared. So that's gonna be this pattern where I'm gonna have u equals a secant of theta. So when I look at that, I see my a is equal to 2, my u is just equal to x, right? So when I make that initial substitution step, I'm going to go u equals, so again, a is equal to 2, u is equal to x. And so it's u equals a secant of theta. So that means I'm going to go x equals a, that 2, times the secant of theta. So I got to make sure I got those initial steps down. And then we're going to take the derivative of that, right? We're just going to take the dx. We know the derivative secant is going to be a secant tangent. And now we're about to do item for item substitution. So I'm going to rewrite this integral. The x's are about to be gone. I'm having nothing but thetas in there. I'm going to insert the trig into this problem. So I got this giant square root. My x is that 2 secant of theta. So I'm going to take that 2 secant theta, plug it in for both of those x's right there. So when I square it, I get a 4 secant squared theta minus that 4. And on the bottom, I got that x, which is that 2 secant of theta. And then I'm going to remember to substitute for that dx part right there, which is that 2 secant theta tangent theta. Tag on that d theta. And I'm noticing that I have a 2 secant of theta on the top and the bottom. So boom, those are gone right away. So I got to make sure remember that tangent right there. But again, you're always going to have a parentheses or a square root of some sort where you're going to go inside there and simplify that square root or the parentheses part. So we know, I usually do that like right here, right above. I'm kind of out of space. So I'm just going to go to the side and do that. If I factor out the 4, I got a secant squared theta minus 1. And then let's remember our Pythagorean identities from the last section. We got our Pythagorean identities right there. You can jot those down again if you need to. But that means when I see this secant squared theta minus 1, that's equivalent to the tangent squared theta. And then you gotta be careful because that's still underneath that square root. All right, so since it's underneath that square root, that's gonna put that as 2 times the tangent of theta. So this became 2 times the tangent of theta. But you should show all that work there somewhere. Just kind of do that right there off to the side a little bit. So now you have 2 times the tangent of theta times this other tangent of theta. So common mistake is sometimes people don't gather everything that they should be, and then they're integrating the wrong thing. So just be as neat as possible with that. But I'm allowed to pull out 2, and I have tangent times tangent to get me this tangent squared theta. And then you got to remember from when we first learned integrals, you can't integrate tangent squared. But what you can do is you can use your Pythagorean identities and you can turn it into secant squared theta minus 1 because you can integrate a secant squared, right? So when you integrate a secant squared, you're going to get tangent of theta because the derivative of tangent is secant squared. When you integrate 1, don't put an x down. This is in terms of theta. We got a d theta right there. So you're going to do theta because the derivative of x is 1, the derivative of theta is 1, and you got your plus c. All right, now I know I'm going to I can distribute the 2 at the end and clear out the parentheses, right? But now I'm on the part of the problem where I'm trying to get my thetas back into the problem. And this is different on this one because I have a single theta there, because the last example we had the cotangent, so you're just going to use SOHCAHTOA. So anytime you have a trig function, use your easy SOHCAHTOA. But if you got a theta, that's the new stuff that I got to show you how to handle that on this problem, all right? So what you're going to do to get your x's back in, same thing each time. You're going to go back to your initial trig substitution step, and you're going to isolate that trigonometric function, all right? So I want you to solve that. You're going to get secant of theta equals x over 2. And then I kind of like that cosine function a little bit better than that secant function. It's a little more familiar to me, all right? So I'm going to make that cosine of theta equals 2 over x. I'm going to draw my triangle right there. All right, and then so cosine of theta is going to be the adjacent side over the hypotenuse, and I can use my Pythagorean identity. I'll do this side squared minus this side squared. Use my Pythagorean theorem. Get that's going to be radical x squared minus 4. Notice I do got a radical x squared minus 4 in there. All right, so then you're going to just use SOHCAHTOA for the first part. So we know tangent is the opposite side over the adjacent side. And then here's what I need you to do with theta, okay? If I gave you this equation last year and I said solve that for theta, what would you do? You would do the inverse cosine of both sides. But the inverse cosine this year is the arc cosine of both sides. So when I do the inverse cosine of the arc cosine of both sides, I'll get theta equals the inverse cosine or the arc cosine of that 2 over x. So just about, every time you got a single theta there, it's going to be one of the arc trig functions right there. So I almost always just go back to this trig function that I use to draw my triangle. I just do the arc cosine of that, and then, or the arc, that trig function of that thing right there. So I'm going to make this arc cosine of 2 over x. And I got that plus c. Now we should just kind of distribute, get rid of that parentheses so we're all getting the same answer. So I'm going to get this radical minus 2 arc cosine of the 2 over x plus c. Now, when you're doing that theta part, so when you have a trig function, you're always going to use SOHCAHTOA. When you're doing this theta part, you're always going to do one of the 6 trig functions right there, arc cosine. This is not a unique answer. If I wanted to, I could have did arc secant of x over 2. I could have written arc sine of opposite over hypotenuse, this thing over this thing. I could have done arc tangent of opposite over adjacent like there. So any of the 6 trig functions is going to work right there. Just kind of pick one and go with it. But I almost always just go back to that one I used to draw my triangle on and just kind of go from there, right? So there's our final answer on that one. If you want another example, I do have another example just kind of worked out here for you. So if you wanted to, you could just pause it and just kind of write down another example. It's actually a little bit neater. I did my substitution steps there, did my item for item substitution, got something I can integrate it, and I always just kind of go to the side and have my substitution side, my triangle based off of right there. So if you want another example, very similar problem there. I think it's easier than the ones that we just did though. So just even you can practice that on your own, so you can kind of get that. All right, we're done working out full examples, but there's two other things that's going to happen when you're working out these assignments that I got to talk to you about, and then we're good. All right. If you encounter inside the integral somewhere, your u isn't always just going to be equal to the x. Let's say inside your integral, you get a 16 plus 25x squared, where your a is the number part that's being squared, and your u is your variable part that's being squared. So you got to know the patterns there. Notice that it doesn't say your pattern, it doesn't say your substitution step, it doesn't say x equals, it says u is equal to. All right, you got to put u equals a times the tangent of theta, right? So on this problem, I would have to put down 5x equals 4 tangent of theta. Like that would have to be my initial substitution step right there. Whatever your u is equal to, go u equals a times tangent of theta. That doesn't really change the nuts and bolts of the problem there. The only thing it changes is one more step. I would make this x equals 4/5 tangent of theta, right? I would still solve that for x, and I would find the dx right there. I would go, hey, the derivative tangent is going to be secant squared, and then I would go about my business, go and do that item for item substitution. And you just got to deal with a little bit more fractions right there. But you guys are the smartest kids in the school here. You can handle fractions right there if it gets a little bit messy like that. All right, and the last thing that I got talked about that gives some people some issues sometimes. Here's what I want to do. Sometimes what we're going to encounter in this section is the sine of 2 theta and the cosine of 2 theta. Now, really important. The only time I'm going to consider using these double angle formulas, if I am at the end of the problem, drawing my triangle, trying to get the x's back in. That's it, all right? You don't want to use these too soon because you're going to make the problem a lot more worse and a lot more complicated and sometimes impossible than what it needs to be, okay? So if I'm right here, so let's just pretend for a second, all right? Let's just pretend right here, instead of right here, instead of me getting a tangent squared theta, let's just pretend that I got a cosine of 2 theta. I haven't integrated this thing yet. I'm not on the part of the problem where I'm drawing my triangle trying to get the x's back in. So I'm not even thinking about using those double angle formulas, right? I'm just going to integrate this sucker. We know when we integrate sine, when you integrate cosine, you're going to get the sine, right? But if your u is equal to that 2 theta, your du is equal to 2, you're going to balance that with the 1/2. And then this 2 is just out there. So then boom, those cancel out. And so now you get sine of 2 theta for your integral answer. And now, so it's like a kind of like right there, where now I was on the part of the problem where I'm drawing my triangle, trying to get the x's back in. So now, once I integrate, I'm done with the calculus, I'm done integrating, and now I'm on the part of the problem where I'm going to draw the triangle, trying to get the x's back in. That's why I'm going to use my double angle formulas, because if you think about it, your triangle up here is a theta, not a 2 theta. And remember from your pre-cal days last year, the sine of 2 theta is not equivalent to 2 times the sine of theta. The sine of 2 theta is 2 sine theta cosine theta. So when you're on the part of the problem, you're drawing the triangle trying to get the x back in, you know your triangle up there is a theta. So I'm just going to put that down here so I don't have to keep messing with that. All right, but you know this is your triangle. You got your theta. You got this, right? And now when you go to do that, like I said, that's a theta, not a 2 theta. So that's when you're going to use the double angle formulas, only in that instance right there. You don't want to use it right here, because if you plug in that, if you make this cosine squared minus sine squared, you know how to integrate that. You know what you're going to have to do? You're going to have to use 2 separate even identities, and you just made that problem a million times worse than it needs to be. Forget all that, right? So just do your integral first, and then once you're done with that calculus, then do those double angle formulas right there. So then you would just do a SOHCAHTOA, right? Sine of theta would be opposite over hypotenuse, and then the cosine theta would be adjacent over hypotenuse, and then that would have given us, we got a 4, we got a radical right there, got that x squared, and then you got that plus c. Boom. Very important section. Please practice that. It's going to be very important. It works in a lot of different scenarios for us there. So we're going to need to make sure we know that stuff there. Trig substitution, really important section there. Get it.